Hello, it is Dr. Jenkins, and here we are for our next chapter. We are going to move right into the respiratory system. So we finished with the cardiovascular, lymphatic, immune, and we're going to kind of take a little detour here to the respiratory system. In this first video, I want to talk mostly about the anatomy. And then in the subsequent videos, we will spend much more time on the physiology. This chapter can get tough, okay? When we get to the physiology of ventilation, of gas exchange, of the oxyhemoglobin dissociation curve. So it gets a little tough. So you can do it. You're just going to have to spend time, okay? So in this first video, as I said, we're just going to focus mostly on the anatomy to give us a foundation that will allow us to then go into the physiology. I have some fact or fiction just to start things off. These things will never be on an exam, but it's kind of fun. Usually when we're in person, I'm able to bring up the answer one by one, but here you can already see the answer, so it's a little spoiled. But you can see the first one is true. People under the age of 30 are able to take in twice as much oxygen as an 80-year-old. So our respiratory system begins its decline, albeit slowly, pretty young. The surface area of the lungs is the same as a football field. Well, not quite a football field, but the Merriam text says that if you were to lay out all of the airways, it would have the same surface area of an entire tennis court, which is still a lot, my friends. The respiratory rate is, as a whole, in most cases, faster in children and women. Usually smaller organisms, even if we look in the animal world, smaller organisms have a faster respiratory rate than larger ones. It is true that we remove a lot of waste through breathing. And this is something that people may not think of as much. I'm going to get a pink color. I think it'll be better against a gray background. Sometimes we don't think about the respiratory system as involved in getting rid of waste, but boy is it. And of course, we're talking about the waste product of CO2. It is not true that, this is kind of worded weird. Let me just read the statement first. It is impossible to climb Mount Everest without supplemental oxygen. It is actually possible. Crazy people. All right, that was all extra, but here's the outline. So like I said, in this first video, I want to spend most of the time talking about the functions and then the anatomy. And then in the subsequent chapters, we'll get into the physiology. All right, folks, you know about the respiratory system. We have what's considered an upper respiratory tract, and then we have a lower respiratory tract. And then we also have some associated muscles that help us breathe, the diaphragm and the intercostals. We know, you know this, that the respiratory system works closely with the cardiovascular system and the urinary system. I thought I had a slide next, but I don't. So how does the cardiovascular system work with the respiratory system? You know this one. We know that we have to bring in oxygen, goes to our lungs, and then that oxygen is pumped back into our heart. And then our heart pumps that oxygen-rich blood out to the body. So we know that our cardiovascular system works very much with our respiratory system. The cardiovascular system is the pump, the heart, which pumps out blood throughout the body. But we have to put into that bloodstream oxygen, and we bring in oxygen through our respiratory system. But then the question is, how does the respiratory system work with the urinary system? And I would like you to know these two. And the answer is they both excrete waste. I think I need an even lighter pink. That be better? Yeah. Both the urinary and the respiratory systems play a role in excreting waste. The respiratory system excretes CO2 as its waste product. As we're going to find out in this chapter, even a small buildup of carbon dioxide in our body can lead to serious problems. And of course, the urinary system, what kind of waste does it excrete? It excretes urea, for example, many others, but it does so through urine. So even though there's not maybe a direct link, if we talk about the cardiovascular and respiratory systems, there is a direct link because the heart pumps blood to the lungs where it picks up oxygen, and then the lungs pump blood back to the heart to be pumped out to the body. So there's not a direct link between the urinary. It's not like the kidneys are connected in some way to the lungs. Of course not. But they both share a really important function in excreting waste. And because they both excrete waste, they also help to regulate pH. It is through excreting that waste that both of these systems regulate pH. As a matter of fact, we're going to talk about this later in the semester. We have a whole chapter on fluid balance and pH balance. And guess what? What are the two systems that play a role with pH balance most specifically? You got it. Respiratory and urinary. Pretty cool. Okay. Let's talk about the functions of the respiratory system. So we know that it works with the cardiovascular and urinary. We know that the respiratory system is composed of an upper and lower respiratory tract, as well as some muscles. But let's be specific. The respiratory system's primary function, the one that you are aware of, is that it supplies the body with oxygen and it gets rid of carbon dioxide. So it's all about gas. Not that kind of gas, haha, like if you had Taco Bell. Please don't have Taco Bell. You'll regret it later, right? So the respiratory system's, one of its major functions is, of course, to bring in oxygen and get rid of carbon dioxide. Why? Well, we just talked about CO2. The reason we need to get rid of CO2 is because it is a waste product. If CO2 accumulates, it will turn the blood acidic in a heartbeat. As we're going to find out later this later this chapter, in the physiology part that I love so much, a 10% increase in CO2 in the blood, right? Let me say that again. A 10% increase in CO2 will cause our respiratory rate to double, because that's how serious it is. Our respiratory rate will double in an effort to get rid of that excess CO2. So our body does not mess around with CO2. And then, of course, we need oxygen to go to the heart and then be pumped out to the body because we need it for metabolism. We need it for our cells in order to work. Right? If we think about our cells all over our body, muscle cells, nerve cells, skin cells, you name it. Our cells, not only do they need glucose, they also need oxygen. So we need oxygen to bring in from the air through the respiratory system to supply our cells with oxygen so they can work. So I've broken down this above function. So in order to bring in oxygen and expel CO2, in order to do that, there's a series of 4 processes. And I've put this together in order. So we first ventilate. I'm having a hard time seeing these. Apparently I'm really wed to using pink. Is blue better? Blue's better. There we go. So these are in order in terms of chronology. So we first have to breathe. That's going to bring in the oxygen and expel the CO2. Then we have a process called external respiration, where oxygen gets diffused actually. Oxygen gets moved from the lungs into the bloodstream, where it goes to the heart, gets pumped out, and we can transport that oxygen in the blood. Then we have a second gas exchange at the tissues, where now that oxygen moves out of the blood into the tissues, where it's delivered to the cells, its final destination. So we're going to talk about that more, but those are the 4 processes that have to happen in order. To do what's at the top, bring in oxygen and breathe out CO2. All right, don't laugh, everyone. I put together a picture, and even though it may look kind of crazy, my goal is to actually make things easier, but will it? I guess the only way to find out is to do it, and you'll have to let me know. So I've color-coded it. So we have first ventilation, then external respiration, number 3, transport in blood, and number 4, internal respiration. So we can see what has to happen first, and that's ventilation. So look at the red here. What's the first thing that happens? Well, we breathe in. So we breathe in oxygen during inhalation, and of course we're also going to breathe out CO2, but I think it might be easier to first focus on bringing in oxygen. That's got to happen first, folks. Then we have what's in yellow. And now I want you to make sure that you can memorize these definitions. We have a gas exchange called external respiration. You may also hear it called alveolar respiration. I'm going to stick to external. It might be a little confusing, but the reason it's called external is because we just brought in oxygen from the external of the body, from the exterior of the body. So in external respiration, oxygen moves, and I think we're going to see this more later, but I think it will be good for you to memorize this now. In external respiration, oxygen moves. I'm just going to write it out. Moves from lungs. Let me do this a little differently. Oh, I just highlighted something. Didn't want to do that, but I'm glad I know I can do that now. Let's try it again here. Let's get rid of this. Okay, I think I'm ready. Oxygen moves from the lungs into the bloodstream. Okay, so we just brought in oxygen, right? We brought it in through our nose, down our pharynx, down our trachea. It eventually will make its way into the lungs. Well, the lungs, the tiniest air sacs of the lungs, are called the alveoli. And here we have magnified the tiny air sacs of the lung, the alveoli. And each alveolus is covered by capillaries. Right? That's what it says here. Each little air sac, or alveolus, is covered by capillaries. So here we see oxygen. Oxygen leaves the lungs and moves into the bloodstream. Now, whatever oxygen is doing, CO2 does the opposite. So CO2 is going to move from the bloodstream back into the lungs. So CO2 is going to move from the bloodstream back into the lungs. So then we're able to take that CO2 and breathe it out. Take your time with this. I think it would be beneficial to just memorize these definitions. Okay, and then it'll help to settle in. So, external respiration, gas exchange between the lungs and the blood. Here we're saying alveoli of the lungs and then the blood. So you could simplify it and say gas exchange between lungs and blood. So first, we ventilate, we breathe, we bring in oxygen. Then that oxygen makes its way all the way through the airways into the lungs. The second step is we have external respiration, or gas exchange between the lungs and the bloodstream. Oxygen diffuses from the lungs into the bloodstream. Carbon dioxide moves from the blood back into the lungs. And why do these things happen? Well, let me say it again. I'll just add on to the end. In external respiration, gas exchange between the lungs and the blood, oxygen moves from the lungs into the blood. That blood gets pumped back to the heart, into the left atrium, through the bicuspid valve into the left ventricle, through the aortic semilunar valve into the aorta, and out to the body. Can't forget that. Versus carbon dioxide, which diffuses from the blood back into the lungs. And then that carbon dioxide moves up the airways, up the trachea and pharynx, into our nose, and then we breathe it out to get rid of it. Well, I've already kind of spoiled this, so after we exchange oxygen into the bloodstream, then that oxygen is going to be transported in the bloodstream. Green. The heart pumps it out. The heart pumps out oxygenated blood. So we transport gases. And of course, the veins are going to be transporting carbon dioxide back up towards the heart, where it gets pumped to the lungs. The veins are going to transport carbon dioxide, which then goes back up to the lungs, and then we breathe it out. Let's pick it up with oxygen, though. So it's transported, the heart pumps out that oxygen-rich blood, and eventually it reaches the tissues. Here we have our second gas exchange, called internal respiration. You might hear it called systemic. Here we have internal respiration, which you might hear called systemic. It's called internal because now we're inside the body. I mean, we were before, but we weren't getting the oxygen from the outside of the body. This is gas exchange between the blood and tissues. So here we have gas exchange between the blood and the tissues. The tissues could be a muscle. It could be an organ like the liver. Everywhere. This is happening everywhere, okay? So how are these gases moving? Well, let's do white. Let's try that out. Oxygen moves from the blood into the tissues. This is the whole goal, folks, right? This is the whole reason we brought in oxygen from the exterior to begin with. But we had to go through a series of steps before we were able to actually deliver this oxygen to the tissues where the cells can use it. So we're delivering oxygen. It moves from the blood into the tissues, which means that CO2 is going to move the opposite way from the tissues back into the blood. And then that CO2 will travel in the venous system back up towards the heart, where the heart will pump it back to the lungs, and then the CO2 will diffuse from the bloodstream back into the lungs, and we'll breathe it out. All right, look at that. I may have made this more complicated, hopefully not. Okay, these are really important, folks. This is the foundation of the respiratory system. You should be able to define all these terms in order and be able to tell me, for the gas exchanges, what it's a gas exchange between. Is it between the lungs and the blood, or is it between the blood and the tissues? And you should also be able to tell me which gases are moving in which direction. Hopefully, when it comes test time, these should be questions that you know and are able to just bim, bang, boom, A+, 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 straight recall. You like my optimism? Yeah. Now, that was one function. So all of that had to do with one primary function of the respiratory system. That was to bring in oxygen and to get rid of CO2. Well, of course, there's more. I already gave you the other biggie, pH regulation. Big, big, big. I mean, huge. We know how important it is to maintain blood pH. By the way, what is our normal blood pH? Should I sing the Jeopardy music? Do, 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 do. Ha, ha, ha. Our normal blood pH is 7.35 to 7.45. I really don't, it's kind of hard to see all this, isn't it? I'm unhappy with my color choices in this background. You should know this, so it's nothing new, but a review just in case. Our blood pH has to exist, period, exclamation point, has to exist in this range for our body to stay healthy. It takes a lot to do that. And what two body systems do we rely on most? The respiratory system and the urinary system to maintain pH. The respiratory system can maintain pH by getting rid of CO2. The urinary system can maintain pH by getting rid of things such as urea or a bunch of other things through hydrogen ions, through urine. There's also some associated functions. Obviously, we have the voice box, the larynx, so it helps with voice production. We have smell receptors in our nose for olfaction. And also we have some tonsils in and around our airways that help to protect us from pathogens. So review these. What if I gave you a multiple choice question? All of the following are functions of the respiratory system except. You just need to be able to identify, oh yeah, right, okay, there's organs in the respiratory system that help with voice and smelling and protecting us from pathogens. Let's talk about the organization, the anatomy. Now, in the lab, sometimes, because the list of respiratory organs is not hugely long, certainly compared to our next chapter, which is the digestive system, there's not nearly as many organs in the respiratory system. However, that doesn't mean that it's necessarily any easier. So my advice to you is to take time to learn the anatomy. In my experience with teaching this class, people see a shorter list or they just think, oh yeah, lungs, trachea, I got it. And then they don't spend the time that they need to learn the anatomy. So it's not going to be as much as a digestive, but don't underestimate it. Learn the anatomy, folks. We are going to break it up, into an upper and lower respiratory tract. It depends what source, what book you read. Some people will include the trachea in the upper respiratory tract. Other people will include the trachea in the lower respiratory tract. We are going to include it in the lower. So I just wanted to point that out. However, for this class, we're going to use the trachea in the lower respiratory tract. So our nose, larynx, and pharynx make up the upper respiratory tract, and the trachea down to the lungs makes up our lower respiratory tract. You can also talk about the anatomy by function or the physiology. So what we just talked about was the anatomical organization. So anatomically, we have an upper respiratory tract because it's, more upper, more superior. And we have a lower respiratory tract because those organs are, lower or more inferior. So that's an anatomical designation. And you should know that. But we can also talk about the anatomy based on its function or its physiology. And I would like you to know these two. Anytime we're talking about the conducting zone, this only involves movement of gas. The conducting zone actually goes all the way down to the terminal bronchioles of the lungs. This will make more sense once we get to more of the anatomy, but I would like you to know these in addition to the anatomical designation. The conducting zone goes all the way down. In other words, the conducting zone, if I were to change colors here, let's go with black. The conducting zone includes everything right down to our bronchioles. Excuse me. And we can't even, we can't even see the bronchioles because they're microscopic, which means that the respiratory zone is only a very small part of the microscopic lung. So the respiratory zone, the reason it's called respiratory zone, and it might be a little bit confusing, but this is where we have gas exchange in the lungs, by the way. So deep in the lungs, we have these two last main structures, respiratory bronchioles and alveoli. The alveoli, remember, are those air sacs. They look like grape bundles. So the majority, what this is telling us is the majority of our organs of the respiratory system, the nose, pharynx, larynx, trachea, primary bronchi, secondary bronchi, tertiary bronchi, bronchioles, and terminal bronchioles, which we're going to talk about. But the majority of our airways are really only conducting gas. Excuse me for one moment. Right, the majority of our airways are just airways. They're bringing in O2 and pushing out CO2. It is only once we get very deep in the lungs where we do that gas exchange. So functionally, physiologically, we call the zone where we actually do gas exchange the respiratory zone. You'll want to come back to this after we learn the anatomy. It will make more sense. If we break down the surface area of the lungs, we bring in air, it goes down the trachea, gets into the lungs, the bronchi. The bronchi split into smaller pieces, which eventually become the bronchioles. Then the bronchioles split into even smaller pieces, which eventually reach the alveoli. The point is, we have all this branching. And what's the function of branching into smaller? More surface area. I said before that if you were to lay out all of the airways, it would equal the size of approximately a tennis court. That's a lot, considering we're only talking about our airways in our lungs. You don't need to know how many total branches there are. You don't need to know this chart. I'm just making a point that all of those branches, there's a lot of them, help us to increase surface area. And by increasing surface area, we're able to do more of the job of the respiratory system. Pretty cool. All right, you thought you could get away in this anatomy without talking about histology. Well, you were wrong. Histology is everywhere. That's why we had one whole chapter on it in A&P 1. So I just want to take a moment and talk about some of the tissues that we'll see lining the respiratory tract. Now, if I was to give a term to the tissues that line the respiratory tract, I would call it the respiratory mucosa. Fancy way of saying respiratory mucosa. Tissues that line the inner respiratory tract. Further away, we're going to have some smooth muscle. We're going to have some cartilage, for example, covering our trachea, which you already know, that's hyaline cartilage. You remember that. But I'm talking about the inner lining, which faces the actual respiratory tract that air passes through. So the inner lining. Let me even write it down here. That way there can be no confusion. inner lining of respiratory tract. And mostly we're talking about the upper respiratory tract, but we tend to include the trachea with this, so that's why I'm being a little bit more general. Respiratory mucosa, inner lining of respiratory tract. We're going to see all sorts of tissue types, but I want to point out two. One of the things that we're going to see, and this should ring a bell, my friends, from A&P1, we're going to see a type of epithelial tissue called ciliated pseudostratified columnar epithelial. This is epithelial, remember. I'm getting my workout here, changing colors. Hopefully it keeps you awake. And we're also going to see some simple squamous, which is also a type of epithelial tissue. These are the only two I'm pointing out that I'd like you to know. The ciliated pseudostratified columnar, you're going to remember from the trachea. When we talked about this tissue type in the tissue chapter, this was the example I gave you, and probably whoever you had for A&P1 gave you. Pseudostratified ciliated columnar, that is tall cells side by side that have cilia on the top. And we find it in the trachea. And actually, this picture down here, between here and here, this is the ciliated pseudostratified columnar. Tall cells, side by side. It's called pseudostratified because even though it's one layer of epithelial cells, it oftentimes looks like more than one layer because the nuclei are at different levels. But at the top is the cilia. And that cilia is going to help filter incoming air, which is really important. We also have this tissue type in the nasal cavity, which shouldn't be surprising. Everyone knows that they've got hairy noses. Let's just be real. That's kind of the fun of anatomy. You can pretty much talk about anything and it's fair game. So we have this tissue with the cilia at the top also lining our nasal cavity. And the reason why, the cilia helps to filter incoming air. There's no guarantee that the air we're breathing in is clean or pure, so we absolutely need some cilia that line our inner lining of our respiratory tract, particularly in the nasal cavity and the trachea, to help filter all the particulates that we don't want in our lungs out. And then once we get deeper into our lungs, in the alveoli, we're going to see simple squamous epithelial tissue. So our alveoli are these grape sacs, right? This is where gas exchange takes place. Well, it should be no surprise that lining the alveoli or the grape sacs would be simple squamous epithelial tissue. We want thin tissue there. Why? Because we need a thin tissue to allow for gas exchange. Oxygen is going to diffuse out into the blood, and CO2 is going to diffuse from the blood back into the lungs. It wouldn't make sense in the alveoli to have a thick epithelial tissue. Then we wouldn't be able to diffuse gases between it. And it should be safe to have a thin tissue here because by the time we get deep into the lungs, all the foreign particulates have been filtered out by the cilia in the nasal cavity and the trachea. And of course, the cilia is located on top of the pseudostratified columnar epithelial tissue. Good stuff, right? I'm not sure about you, but as I'm recording this, even though you can see the day, it's February, the sun is shining. That's because life is good anytime we're talking about anatomy and physiology. All right, here's what we'll do. We're going to finish this. We still have a little bit to go, but for the rest of this first video, what I'm going to do is I'm going to go organ by organ through our upper respiratory tract and our lower respiratory tract. We're going to talk about the basic structure and the basic function. Try and keep it pretty simple, okay? Basic structure and basic function. Excuse me. So, let's start way at the top, which is the nose. You don't really need to know, at least for lecture. In lab, you'll get into more of some of the details. But just for lecture, let's keep it simple. I mean, everyone knows what the nose is. We may remind ourselves that most of the bottom part of the nose here is cartilage. And there's a bone at the top. So your nasal bone is only at the top. And you can feel that on yourself. The area between your eyes is bone. It's hard. But then the rest is cartilage. The nasal septum is what divides the actual opening between your nostrils. You need to review all of the functions of the nose. This is particularly important. Obviously, we're going to bring in air. So one of the functions of our nose, I mean, let's just keep it simple. Bring in air, breathe out CO2. That's obvious. But when we bring in air, it's important that we begin this process of warming the air, cleaning or filtering it, which we just talked about because we have that specialized ciliated tissue to help filter the air. So we need to warm it, filter it, and humidify it. Humidify means to add moisture. Because what we're beginning to do here is we're beginning to prepare the air for our lungs. And the conditions that make for best gas exchange at the lungs means that the air is warmed. We can more easily diffuse warm air. Obviously, it's clean. We don't want bad stuff getting to our lungs to clog it up. And that the air is humidified. I'm just going to walk to the other room here because I feel like I've been sitting all the time. Can't sit so much. We're going to stand. Perfect. So by adding a little bit of moisture to the air along the respiratory tract, this is going to make for the best possible conditions down the road once we get to the lungs for gas exchange. Of course, the nose can also help us detect odors. We have specialized nerve endings for smell, and it begins to act along with other organs as a resonating chamber that amplifies our voice. So know all of them, but I put an extra special asterisk beside the top one. Warm, clean, humidify. I just like this for a perspective. We have a model in the lab that looks just like this. Let me see. Okay, so we can see the entry point of the nose, obviously. And we're going to see that the air is going to continue through the nasal cavity. So the part that we're going to be talking about next is the nasal cavity. Cavity inside the nose. And I also have to the right a cadaver where they've made a cross-section in the sagittal plane. It's just an interesting perspective. It might be a little bit gross to you, but it's an interesting perspective to show how everything fits together. So we just finished talking about the nose. Let me use a different color. Let's use blue, right? It's going to lead into the nasal cavity, which is eventually going to go down the pharynx and eventually go into the trachea. Pretty cool view, though, to see how things are pretty smushed together, because in the blue we have the trachea. Right behind that or posterior to it is the esophagus. Then, of course, we have the spinal cord. Or excuse me, that's not the spinal cord. That is the vertebral column. The spinal cord is right in front of it. So we have the vertebral column, and then this is the spinal cord, right? Then we have muscles. It's just all kind of smushed together. It's pretty cool. So I just introduced the nasal cavity. Let's talk about it. The nasal cavity is the passageway that air passes through. I mean, if you think about the nose itself, the nose has an external structure where we have the nasal bone, then we have the cartilage, we have the nasal septum. But the nasal cavity, now we're really considering the passageway inside the nose. That's how I would define it. Passageway inside of the nose. Dramatic pause. Passageway inside of the nose. And there's a lot of anatomical features that are important. And I'm going to recall back to A&P 1, much to your probably discomfort. So you may recall we have these folds in the bone called the nasal conchae. The superior and middle nasal conchae are parts of the ethmoid bone. The ethmoid bone is that big walnut-shaped bone right behind your nose. The inferior nasal conchae is its own bone. But the point is that the nasal conchae are folds in bone in the nasal cavity. And we can see them right here. These folds, so in other words, instead of it just being flat bone, it has contours. It has folds. So the bone kind of comes out, and then there's a depression. Comes out, then there's a depression. The nasal conchae are the folds where it comes out. What is the benefit of having these nasal conchae? You know what it is because it's one of the common answers for A&P. Increases surface area. Because what's lining these folds? Cilia. They're hairy, my friends. So the idea that we have these folds just means that we can fit more cilia in there. And if we can fit more cilia in them, we can do more filtering. And not only is there cilia, but there's mucus. And together, the cilia and the mucus allow us to best filter the air. The mucus is sticky, and I apologize for being kind of straightforward there. But the stickiness also helps to filter and catch things that are coming in. Air is more likely just to breeze right through, but if there's some dirt particles, it's more likely to get stuck in the mucus. All the rest on this slide is extra. Okay, let's see. One more thing that I forgot to mention, and I want to make sure I get everything, is a meatus. So, the nasal conchae are the folds. The nasal conchae are the folds that kind of jut out, right? But the meatus, or the meati, are the depressions in between. So we have three of them: superior meatus, middle meatus, and inferior meatus. So if I was going to define meatus, depressions in between folds. And of course the folds are the nasal conchae. So the actual folds themselves, where the bone kind of juts out, is a nasal conchae. And the depressions in between is a meatus, or meati for plural. All right, so we're going to begin to make our way down the respiratory tract. All right, so we came through the nose into the nasal cavity, And now we're getting to the pharynx. So the pharynx is the region right after the nasal cavity. So I'm going to color in the bottom part. So what I'm coloring in blue is the pharynx. What was before it, in black, was the nasal cavity. So we bring air in, it goes through the nasal cavity in black, and then it will travel right into the pharynx. Typically, the pharynx we think of as the throat, but no, we're not going to call it the throat. We're going to call it the pharynx. The pharynx has 3 regions. The uppermost region, look at this top picture right here. The uppermost region, shown in yellow, is the nasopharynx because it's closest to the nose or nasal cavity. The middle region is the oropharynx in pink, and it's called oropharynx because it's a region that's shared with the oral cavity. And then the most inferior region is the laryngopharynx because it's going to lead us into the larynx or the voice box. There's not necessarily a clear delineation where the nasopharynx ends and the oropharynx begins. These are more like regions. But they are a little bit separate in their function, or their anatomy, I should say. All collectively together, the function of the pharynx is passageway for air. There's no gas exchange happening here. We're simply providing a passageway for air. And just like the nasal cavity, the job of the pharynx is to move air, but warm, filter, and humidify it. What are some of the unique things? Well, in the nasopharynx, we have a tonsil, which is a patch of lymphatic tissue, help us find bad pathogens right away to activate our immune system. The oropharynx is shared between the nasal cavity and the mouth. And then the laryngopharynx is going to lead into the larynx, the most inferior. All right. So we've gone through the nose, the nasal cavity, and the pharynx. And now we are in the larynx, which I'm going to color in as black. So the pharynx leads us into the larynx. I like this picture down below. So in the lab part of the course, where you'll spend more time hammering in the anatomy, I will use this bottom picture because I think it's just better. This bottom picture is like a view if we put a camera down the throat, right? We put a camera, or through the nose, either way. We put a camera through the nose, through the pharynx, and into the larynx. This is what you would see. Well, first of all, what are the functions? Well, the larynx is otherwise known as our voice box. This is going to contain our vocal cords. There's also a very important structure called the epiglottis, which is going to help us keep food out of our trachea. So let's start there. I've circled in red here the label for the epiglottis. The epiglottis is this flap that I've colored in blue. It's a flap of cartilage. And what it does is, when you swallow, it moves down. So let's look at this model. And let's imagine that right now, the person is not eating. So they're able to bring in air. Air moves bloop through the larynx into the trachea. It's fantastic, right? But when we swallow, we need to do something, because the trachea and the esophagus are one in front of the other. And you can see here that there's kind of a shared opening. So if we're not eating, The epiglottis is in the up position. And that's the picture that I'm showing you right now. So when we're not eating, this is what the epiglottis looks like. It's in the up position, which means that air can come right in and air can continue down. But when we swallow, so let's now look at what would happen when we swallow. When we swallow, this epiglottis moves down. The flap comes down, and it covers off the trachea. That way, when we eat, food will go down the right tube. When we swallow, for that moment that we're swallowing, the epiglottis moves down to cover the trachea. And that makes sure that food goes down the right tube. We don't want food in the wrong tube or the trachea. That's a pretty important job. All right, let's talk about the structures of the larynx. So I'm going to use this bottom picture. Let's first start with the opening. The opening itself is called the glottis. And it's a little bit hard to see with how it's labeled, but that's why I get paid the little bucks to help you here. This opening, the opening is called the glottis. Opening, called the glottis. Surrounding the opening are our vocal cords. So we have these two flaps, one there and one here. These two flaps that line the opening or the glottis, these two flaps are called the vocal cords. And what's going to happen is when we push air through the glottis, we will vibrate the vocal cords. And in doing so, we create sound. The vestibular folds are these areas. Vestibular folds. They connect the vocal cords to the outer respiratory tract or to the body. So they're just there as a structure to connect the vocal cords. Vestibular folds, what's in pink? Glottis is the opening. What surrounds the opening are the vestibular folds or vocal cords. Excuse me. See, look. You got me all confused. This is why it's good to review, folks. The opening is called the glottis. Surrounding the opening are called the vocal cords. And the vocal cords are those blue flaps that when we push air through the opening, the vocal cords will vibrate to produce sound. Holding the vocal cords to the rest of the body are the vestibular folds. All right. Here we can see what the vocal cords look like when they are open and closed. So we can move surrounding muscles and cartilage to open or close, which allows us to change the pitch of the sound that we're trying to get out. All right, now, the larynx is a pretty sensitive tissue. So if we look to the outside, all right, so look at this view down here. This is the lateral view. Here is the epiglottis that we talked about. And basically, the vocal cords, here's the vocal cords are like right here. This is why I prefer this bottom picture here, because you can really see. On the side view, the vocal cords just look like a little slit. Well, these vocal cords are pretty sensitive tissues. So as such, we need to have some pretty thick cartilage that surrounds it. So anterior to that, we have a series of cartilage that protect it. I'd like you to know these two. There are some inner cartilages that I'll mention in lab, but I'm going to focus more on the big ones. The big one that you probably know is the thyroid cartilage. Easier to see in men, it's the Adam's apple. This whole blue cartilage piece is the thyroid cartilage. And it's really there to protect the vocal cords. You can, there's if you feel your vocal cords, you feel your upper throat, and you talk, you can feel them vibrating, but there's skin, and then there's the thyroid cartilage. There's not much there to protect the vocal cords. So we have this pretty decently thick thyroid cartilage to protect the vocal cords. And then there's another smaller piece of cartilage below that called the cricoid cartilage. Excellent. There are some inner cartilages as well, but you only need to know these top two for now. Protect the vocal cords and the epiglottis. Now, let's get into the trachea. So what we've done thus far, the nose, nasal cavity, pharynx, and larynx, was all considered the upper respiratory tract. Now we're going to get into the lower respiratory tract. And of course, the first structure within the lower respiratory tract is the trachea. You know the trachea. Windpipe, commonly known as. I've given you the dimensions, but you don't need to know those. However, what I would like you to know, surrounding the trachea are C-shaped cartilage rings. That's what we're seeing here in the front. Cartilage ring, cartilage ring, cartilage ring, cartilage ring. But they are C-shaped, which means the opening on the back, we had a good picture here, they only go around 3/4 of the way. And the back of the trachea is muscle. So we have these C-shaped cartilage rings. I'm going to show you a model in the lab video. We have these C-shaped cartilage rings. But the back, they're C-shaped instead of being O-shaped. If it was O-shaped, the cartilage would go all the way around. But instead, they're more C-shaped. And the back of the trachea is muscle. And the back part of the trachea is called the trachealis muscle. The reason why we have this trachealis muscle on the back has everything to do with the fact that the trachea butts right up against the esophagus. Let me go back to a picture. Let me erase all of my drawings. Okay. So the trachea butts right up against the esophagus. Food is going to go down the esophagus. Air goes down the trachea. So we have cartilage rings that protect the front of the trachea. But the back of the trachea is muscle. So the benefit of having the back of the trachea as muscle is that when we eat a big piece of food and that big piece of food goes down our esophagus, the trachea is able to be flexible. If I eat a really big piece of food, the esophagus might stretch. And the fact that the back of the trachea is muscle means it has some give to it. So that big piece of food that stretches the esophagus might temporarily kind of jut out into the trachea. And that's okay. It only takes a couple seconds to swallow the food. But that's the benefit of having a C-shaped cartilage ring. So for the front of the trachea, because it's very much anterior and there's not much protecting it from the outside of our body except for the skin. So for the anterior part, we get the protection from the cartilage rings. But in the back, we have muscle. so that if we eat a big piece of food, it might jut a little bit out. Well, the muscle can kind of move in a bit. You don't need to know how many C-shaped cartilage rings there are, but I gave you that number just in case. And as we already talked about, the inner lining of the trachea is made up of the ciliated pseudostratified columnar epithelial tissue, which is able to filter out and trap particles. And not only that, but the cilia can all move in one direction, up, to push that foreign particle back up the trachea so you can breathe it back out. And that's what this picture at the top left is trying to show you. So here we see the pseudostratified ciliated columnar, tall cells with cilia at the top. As air is coming in, we filter out these red particles. So these red particles are meant to be dirt, for example. So the dirt gets caught in the cilia, but then if all the cilia move in this direction at once, it has the effect of pushing the dust particles back up, and then we can breathe them back out. On the right here, this is actually what the cilia look like. Looks like shag carpeting from your grandparents' days, my parents' days. I grew up with red shag carpeting in my home. And the cells that produce the mucus are actually called goblet cells, these orange guys. You don't need to know the goblet cells, it's just there as a picture. All right, now we're going to move pretty quickly. So we are going to bring air down the trachea, and then the trachea splits. And that splits into bronchi. We have a right and a left primary bronchi. Of course, we're always going to label the right and left sides as it would be in that person. So this here is the right primary bronchus. This here is the left primary bronchus. Okay, so the trachea comes down, splits into two, the right primary bronchus and the left primary bronchus. The bronchi is plural. Notice the bronchi are structured the same as the trachea. Cartilage rings. A couple other anatomy points to talk about. The carina. There's an elevated ridge right at the separation point. So what I have colored here in blue, that last piece of cartilage of the trachea, right before it splits, is elevated. I don't know that for our purposes it has much of a purpose for us to understand the physiology behind it, but it's there, and I'd like you to know what it is, because you may hear it later. So the carina, elevated portion of cartilage right where the trachea separates into the bronchi. Carina, elevated area of cartilage right where the trachea splits off into the bronchi. Okay, now we're also going to see another term that we're going to see again later called the hilum. You may hear it called hilus. Either way is really acceptable. Well, if you notice from the top, these bronchi enter the lungs, right? We see the lungs, that spongy lung tissue surround it. Well, that bronchi has to go through an opening in the lungs. So this opening in the lungs where the bronchi enter is called the hilum or hilus. We're going to see this term later. We're going to see it, for example, in the kidneys. The opening in the kidneys where the renal artery and vein enter the kidneys is called the hilum. The opening in the lungs where the bronchi and, for the record, the pulmonary arteries and veins, they're going to enter the lungs too. The bronchi and the pulmonary arteries and veins enter the lungs through an opening called the hilum. Opening. All right, now we're going to begin to branch these bronchi. We had the right primary bronchus and the left primary bronchus. Well, the primary bronchi split into secondary bronchi. The secondary bronchi split off into tertiary, what I have the squiggly lines. So we have our secondary bronchi, primary have the arrows, our secondary are the thicker straight lines, and then our tertiary are the squiggly lines. You don't need to know the numbers, but what I want to point out, the primary bronchi are structured just like the trachea. But as we move down, as the branches continue, eventually the covering of the airway, the covering of the bronchi, switches from cartilaginous rings to smooth muscle. So by the time we get to the tertiary bronchi, they are covered with smooth muscle. It is no longer cartilage rings. So the primary bronchi are structured just like the trachea with cartilage rings. But by the time we get down to the tertiary bronchi, now the airway is covered with 100% smooth muscle. Very important. Okay. Now we're almost to the end of this video. I know it's kind of gone longer than I expected with the anatomy, but that's the way it usually goes. Just get so excited. Now we're going to switch to the bronchioles. So the previous parts were all bronchi, right? So what I have in black here, primary bronchi, secondary bronchi, tertiary bronchi. But what's going to happen is the tertiary bronchi are going to branch off into other structures called bronchioles. You're not going to be able to see it on this picture because they are microscopic. You're going to see a slide later where I go through the order of the airways: nose, nasal cavity, nasopharynx, oropharynx, laryngopharynx, larynx, trachea, primary bronchi, secondary bronchi, tertiary bronchi, bronchioles. So we are continuing with the branching of the airways, where the tertiary bronchi branch off into bronchioles. And that suffix, bronchioles, tells us that they're smaller. So here in this picture, now we are seeing a magnified bronchiole. So just this area right here is the bronchiole, right? So the branches, the bronchioles branch off of the tertiary bronchi. They also are covered with smooth muscle. So remember, the primary bronchi are covered with cartilaginous rings, but then that cartilage covering slowly turns into smooth muscle by the time we get to the tertiary bronchi. And the bronchioles are also smooth muscle. And the bronchioles are really important because it is in the bronchioles that we're going to be able to constrict and dilate that airway. Because it's covered with smooth muscle, we can constrict or dilate it. And this is going to be a way that we can alter air flow. Hugely important. When we talk about regulation of airflow, We discussed this in the cardiovascular system, in the blood vessels. We can constrict or dilate blood vessels to create more or less flow or alter pressure. Well, the same principles apply to the airways. Before we had talked about constricting or dilating blood vessels. Now we're talking about constricting and dilating airways. And the bronchiole is a major source of our ability to regulate airflow because it's covered in smooth muscle and it can constrict to reduce airflow or it can dilate to increase airflow. Let's finish our discussion of the anatomy. The bronchioles split off into terminal bronchioles. So what I've put in pink are the terminal bronchioles, which eventually lead into, let me change colors, let's do this, which eventually lead into the respiratory bronchioles, what I've put in this greenish color. So we're just continuing the branching. The bronchioles branch off into the terminal bronchioles, which branch off into the respiratory bronchioles. And it is the respiratory bronchioles that lead into the alveoli. It can be a little confusing. Oftentimes we think of terminal as the end. It's named terminal because it's the final conducting zone. Remember at the very beginning of this lecture, I gave you the upper and lower respiratory tract as our anatomical designations, but then we also had our conducting zone and respiratory zone, our functional designations. The terminal bronchiole is a conducting zone, so it's still just passing airflow. But our respiratory bronchiole is our first area where we can do gas exchange. And we can do gas exchange in the respiratory bronchiole and the alveoli. And because we can do gas exchange there, they're considered to be part of the respiratory zone. Excellent. All right, well, what I'm going to do is I'm going to end here, and then we'll finish the rest of the anatomy in our second video with the alveoli and the pleura, and then we'll continue from there. But please, please, please look over the anatomy well, and it will help you better understand the physiology. All right, thank you, everyone.